So I will spend a few words to introduce the speaker, who has been elected, by the way, by the board of directors as the speaker of this year. This is an election. We have different proposals, and then the board of directors, as is 15 people, they do meet and they decide who is going to be the next speaker. Just to tell you the entire truth, I have to say that this year is very special because Chris was already selected as the speaker for last year. But then he was in the same days, he was already busy in China, if I remember well, or some, yeah, in China. So he said, I'm very sorry, I would be very pleased to lecture for you, but I cannot. And for us, it was so important to have him with us that we decided to postpone it. And okay, and that's this is where we are today. So Chris, I studied a bit. His CV was not difficult because you find a lot of information about him on the web. I discovered that Chris was born in South Wales, UK, and that was some time ago, sometime in the last century. I will not say when. But then he also has a Dutch nationality because, in fact, he has been living for quite a long time in the Netherlands, almost 40 years, if I'm correct. So there were less than 30 years in the UK and less than 40 in the Netherlands. So you have been longer a Dutch. I don't know whether a Dutch citizen, but somebody living in the Netherlands. Chris obtained a bachelor in geology at Imperial College London, and then he obtained a PhD again at Imperial College in 1982. There was 1 year that he spent at Berkeley, and then he started his Dutch journey. He was postdoc, assistant professor, associate professor, and then finally full professor. And this was at the University of Utrecht in the Netherlands. He's still there. He's a professor of earth materials and experimental rock deformation since 1994. 1994 is the year in which I obtained my PhD, Chris. So it's an important year for both of us. He also has been for the last 10 years or so a guest professor in China at the Institute of Geology in Beijing. Well, if you go through his scientific record, that's quite impressive. So I'm not going to reveal your H index because it's very high and because I don't trust the H index anyway. What I would personally say is that it's you have an impressive number of significant publications. They are impressive not only because there are so many, they're impressive because they are illuminating at times. They've been really paving the way to other researchers. And then there is a number of prizes and awards, and I think this should be mentioned because they give an idea about recognition that you have. So I could see already a UK Watts medal during your bachelor. That was quite a long time ago. But then you got a Royal Dutch Shell Prize that was awarded by the Royal Dutch Society for Sciences for contribution to experimental rock deformation. And then a beautiful medal from the EGU, the European Geosciences Union, that's more recent, 2017. That's the Louis Nel medal. Louis Nel is a name that everybody would know. In Grenoble is particularly well known because he was one of those people who contributed to the creation of what we call today the campus in New York, including the synchrotron, etc. Well, I found a very nice collection of things and comments about you in the motivation for your when they awarded you the Louis Nel medal. And for example, they say that your contribution has been seminal to understanding the formation and frictional slip associated with solution precipitation processes, what we also call pressure solution processes. You've been making outstanding contribution to the long-term creep behavior of rocks, the effects of fluid rock interaction, the frictional properties of faults, the potential effect of CO2 rock interactions, the deformation behavior olivine and calcite, etc., etc., etc. Now, You have a prominent scientist, that's very clear, but you also have a fantastic professor and a supervisor. Because these young men that you see on the screen did supervise over 90 master projects, and he supervised 40 PhD students, of which 6 still ongoing. These are big numbers, and to us, to the alert community, these numbers are more important than your H index, Chris. Our job is not only writing papers and getting your H index to be, to increase, but it's also supervise younger people and educate them. And in this respect, I find that this part of your CV is extremely interesting, and I find it spectacular. Not only we are researchers, not only we are teachers and supervisors, but we all also serve the community. And also in that particular box, you are doing pretty well, because you have been leading a number of things. You have been managing and leading the experimental rock deformation group in your university. You are the head of what is called the HPT laboratory. HPT stands for high pressure and temperature. So I guess there is quite a lot of pressure on you as the high pressure and temperature lab, etc., etc., etc. Dean of this, director of that. I don't think that it makes any sense to list all these achievements, because
No,
you can
please
find
don't.
but again, but it's important they are there. All these things together, they speak of somebody who really devoted and is devoting his career to research, to education, and to service to the community. So that's a great CV, and I'm very proud that you are with us today. So Chris, without wasting any of our time, I think that we are ready to and looking forward to listening at your presentation. If you can make it in about 50 minutes, as we said, that would be great. And then afterwards, we'll go for questions and discussion. Again, we'll be recording this session. I know that for Chris, that's fine. If any of you doesn't want to be recorded when he or she asks questions, just let us know. With that, it's my pleasure to give the floor to Professor Christopher, alias Chris Spiers. Please, Chris.
Thank you very, very much, Gino. I just tried to share my presentation, and I shall respond to your wonderful introduction. Share application screen. Now in application window, here it goes. And if I go to full screen, right, do you see my screen?
Yes.
Thank you very much indeed. Well, Chino, thank you for the extensive introduction. My God, I hope I can live up to that. It's a very great pleasure and honor to be invited to give this talk in your network, which is contains people and students of astonishing quality. It really is impressive. You know, science, why do I do it? Actually, I do it for the young people because that's what I really get excited about. So the only thing I regret about today is that we're not in a class where I would be able to talk far too much to as many people as possible, especially you young scientists. That's what makes it all worth it for me. Okay, so geomaterials, the behavior of geomaterials controls how the Earth responds to stresses induced by tectonics, by gravity, and by human activities. And I'm going to talk today about the rock and fault mechanical properties that influence induced seismicity in the Groningen Gasfield in the Netherlands. So, you know, we're all in the Netherlands this afternoon with Stefano as well. But I'm going deeper than people, down 3 kilometers to talk about induced earthquakes. So, let me give you a little bit of an introduction to the Groningen field for a start. Here is the Netherlands. I'm just going to switch my pointer to the laser pointer. Okay. Here is the Netherlands, and here is the Groningen Gasfield. It's enormous. It's the 7th largest onshore gas field ever discovered on Earth. It's been producing since 1963, operated by the company NAM, which is a Shell Exxon joint venture. It has enormous economic importance for the Netherlands. It has had over the years, and producing so long, of course, it's very highly depleted. Still contains about 20% of its original gas, and it still makes it somewhere in the top 20 of largest gas fields in the world, even though much of the gas is gone. Let's have a look at it. So let's take a look through this cross section here, northwest to southeast. Here is the reservoir. It's a sandstone located at a depth of about 3 kilometers. And that sandstone is a Permian, Aeolian, alluvial fan body. It's quite thick, 100 to 250 meters thick, mostly. And that means that the vertical stress is about 65 MPa. The original gas pressure was about 35 MPa, so roughly hydrostatic, and it's now being depleted by production of gas through the many, many wells to about 8 MPa. When this gas comes out of there, it goes all over Europe, or it has done in the past. Now, right above the reservoir, if we look at it here, you see this dark brown layer, which is a claystone, and a big thick packet of evaporites, carboniferous shales and coals underneath the reservoir, which are the source rock. That's where the gas comes from. It's trapped under all these evaporites. Now, producing gas for this last 50 or more years has had some effects, of course. The first effect to be noticed was subsidence. So producing gas from the field has led to this subsidence bowl, and the deepest part of this is now around 35 centimeters. There's a different contour representation here with some earthquakes marked on it. So it's quite a substantial amount of subsidence for a country which is already, at or below sea level. So this has been going on steadily with time and with depletion of the field. Subsidence itself is not necessarily that much of a problem. What has become much more of an issue is induced seismicity. And here you see the gas production history since the field began, and there was no induced seismicity detected until the early 1990s. And then you see an increasing frequency of events. This is the recorded number of events, increasing frequency with magnitude greater than 1 and increasing magnitude. That seismicity is concentrated in the areas where the subsidence is the greatest. Okay, here you see some earthquake events marked. So this is where most of the earthquakes occur, where the subsidence is greater, which actually corresponds to where the reservoir has compacted the most. The biggest earthquake so far was in 2012, magnitude 3.6 earthquake, which is very small, but still these earthquakes have substantial effects in the Netherlands. They're shallow, the ground is soft and very sensitive to these earthquakes. If they cause damage, and in a country where you don't have natural earthquakes, or a part of the country where you don't have any natural earthquakes, this is deeply disturbing to people, and they get, of course, very upset. Now, how will these earthquakes occur? Where are they occurring is the first question to ask. The very latest data, which started to emerge after that 3.6 earthquake, which upset people very, very greatly, latest data since then has been obtained from a lot of activity going down new seismic networks. So the company NAM, the operator, established a new seismic array together with the Meteorological Institute in the Netherlands. Here you see these seismic stations, and that enabled the hypercenters of induced events with small magnitudes to be detected much, much more accurately. And you can clearly see here that these fall on fault, and there is absolutely no doubt about that. Now, excuse me, these earthquakes are clearly correlated with faults that cut through the reservoir system. Now, after the large earthquake in 2012, the operating company started a massive research program under pressure from the government, of course, but with a very, very serious scientific effort involving many, many different institutes and universities. They approached us to investigate two things: compaction behavior of this reservoir sandstone and relationship between that and fault reactivation. So what is reactivating these faults to cause seismic activity on them? So the mechanical properties, the properties of these sandstone geomaterials and these fault rock geomaterials, okay, having data on those is absolutely crucial for modeling the system behavior, of course. Our task, we were asked to try to understand what are the controlling physical and chemical processes that actually operate in this reservoir system, which is faulted. Yeah? What are the processes going on there under real in situ conditions? Okay, so this is a couple of shots of our lab with the stuff that we use to do a lot of experimental work. So let's get now a bit more into the nitty-gritty. So how is reservoir compaction linked with induced seismicity? Here's a cartoon of such a reservoir, okay, cut by faults. Of course, when you start to produce gas from a system like this, the pore fluid pressure drops. So the vertical effective stress increases and the rock starts to compact. Now, that compaction, of course, sets up a stress-strain field, gradients in stresses and strain around all these faults. And that in itself will determine how the stresses on the faults evolve and whether they'll be reactivated. So that's the link between compaction and activating earthquakes on these. This is where the earthquakes occur on these things. Okay? And it's because of the offset and the depletion of the reservoir, which is deforming. Okay, now, so how does that reservoir deform? It's an absolutely crucial question. And of course, it's a porous sandstone. Of course, there are poroelastic effects. And those can be easily quantified. We know about poroelasticity. What about permanent inelastic deformation or plastic deformation of the reservoir? How important is that? How would permanent compaction change the stress-strain field distribution around here? How would it change the amount of energy that is stored versus dissipated? And how would these changing stress fields lead to forcing of faults to become active and to produce earthquakes? Those are the questions we try to address, and these are my students and postdocs who actually did all the work while I did all the talking. Okay, so compaction is driven by pore fluid pressure decrease is a key driver for changing the stress field. How we have to quantify that compaction behavior. We need to know, is it elastic or do we need another constitutive model? So to find out about that, we did lots and lots of experiments on cores taken right from the seismogenic center of the field, from this region here, the cores being taken in 2015 by the operating company. Here you see it all happening. And we did lots and lots of conventional triaxial compression experiments on these reservoir sandstone samples in many different configurations: compression tests, relaxation tests, hydrostatic loading experiments, and stress cycling experiments, using samples covering the full porosity range of the field. The lowest value is about 12%, the highest value is about 26%. Constant strain rate experiments, mostly in which we simulated depletion conditions in terms of stress, effective stress development. Temperatures were the real reservoir temperature, which is about 100 degrees, and a real pore fluid in the pores. So a simulated 4 molar saline brine, which actually makes a difference. I'm not going to talk about that today, but the pore fluid actually has effects. So we simulated depletion of the field using different kinds of boundary conditions and so on in our triaxial tests. Now, I'm only going to talk about one very, very nice set of experiments today to give you a picture of how this stuff behaves. I'm going to talk about stress cycling experiments that we did on these sandstone samples. I'm just going to illustrate it with two experiments. So in this plot, this is a plot of the mean effective stress applied to a sample against porosity reduction, the compaction of the sample, the loss of porosity that occurs during loading by increasing the mean effective stress. These experiments were performed initially at hydrostatic loading, and from 40 MPa onwards, the sample was deformed axially, so increasing the differential stress, so dioric loading. Two sets of data here are for these two samples, which come from right next door to each other in the same piece of core, just right exactly next door to each other. They're sister samples. This one, that's the red curve here. And you see this loading curve, this monotonic loading curve, very linear in this portion here. And then you see failure starting. And this is then deviatoric unloading, so unloading, removing the axial differential stress, and this is then removing the hydrostatic stress. The black curves were obtained from this sample, the sister sample. And what we did in these experiments, we did not monotonically load the sample, no, we cycled loading. Okay, so we load up, unload, load up again, unload. And you see all these cycles also in the deviatoric loading part. What is happening here? What you see is that you're getting unloading, reloading along the same path. That's elastic. In that initial increment, you've accumulated permanent deformation, and that happens in every cycle. So you have elastic unloading, reloading, and unloading, and permanent deformation. What does that mean? It means that every cycle here is accumulating elastic deformation and permanent deformation, and every time you re-establish the stress, in effect, you are reaching a yield point in which you now get an additional increment of permanent deformation alongside the elastic strain that goes with the increase in stress. So essentially what you're seeing here is increasing yield stress, if you like, following and some sort of expanding yield envelope. The fascinating thing is correspondence between the two sample curves here, the envelope here, the outside, the red curve, and the envelope to the black curve. The correspondence is almost perfect, which means that this procedure of cycling load does not actually influence the behavior of the sample. So for each yield stress that we move back to in cycling the load, we know how much permanent strain has been accumulated. Okay, so we can subtract the permanent strain from the total strain and get the elastic and the inelastic strains independently. And for this particular pair of samples, here you see the inelastic strain that is accumulated during this loading path. Okay, so it really is amazing that this cyclic process does not influence the behavior of samples. It's very, very important because it allows us to be able to track the behavior of samples and right up this curve, separating the inelastic and elastic components independently from each other, knowing that we're not damaging the sample in some way which makes it not representative. The amount of inelastic deformation occurring here, alongside this, is obviously non-linear reversible behavior here and much more linear here, is up to 30 or even 60% of the total strain. So 30 to 60% of the mechanical work done in deforming the sample is actually dissipated in these experiments, which essentially simulate depleting the gas pressure in the reservoir. Note, how linear this portion is. Note also, it's linear, yeah, that smells like elastic behavior, but no, it's not. It's 50% inelastic. Okay, so all that is linear is not elastic. Okay, so which bit of this data is relevant to the field? Now, this type of behavior, this sort of shape of curve, seen, here it is, look, it's the same shape, seen in sandstone experiments where you plot mean effective stress against porosity reduction. It's very commonly seen in experiments in sandstone. It's called three-stage behavior. The vast majority of experimental work that has been done on sandstone has actually looked at stage 3 behavior, where you're talking here about strains and compactions that are in the region in excess of 1 or 2 or 3%. Okay, this is the region, this linear part. Those are the mean effective stresses and the amounts of deformation that actually correspond to the conditions in a gas field like Groningen. If one got into this region, you'd be seeing vast amounts of subsidence. The Netherlands and Groningen would be gone. Okay, so this region is where, from previous work, we know you get failure of the samples, crushing of the grains. What is happening in here? And what is happening in here? Well, this stage, this, I'm not going to explain how we know this now, but this is a region where cracks associated with getting the drill core out of the ground, preparing the sample, these are being reclosed. Round about here, you reach a mean effective stress, which is the in situ value from where the samples came. And from that point on, you get this linear behavior. This is the bit that's relevant to the field. It's linear, but it's not elastic. Although in many modeling studies of reservoirs, this type of behavior is simply assumed to be elastic, but in fact, in Groningen, it's 30 to 60% inelastic. So the question is now then, can we quantify this type of behavior? And this is how we did it. These are differential stress against mean effective stress, basically QP plots, okay? And what you see here are these series of data points, are these cyclic loading experiments, going individual experiments in one run, going up to increasingly high stresses. And at each point, we can measure the amount of permanent deformation independently of elastic deformation and express that permanent deformation as a permanent compaction, permanent loss in porosity. So we know porosity development along these lines of data from individual load cycling experiments in the differential cycling field. If we know the compaction volume changes in porosity, we can contour them. And that's what we've done here, is essentially contour the amounts of porosity reduction occurring as a function of differential and mean effective stress. This is for a low porosity sample, a medium porosity sample, a high porosity sample. And what you immediately see is that the yield envelopes for these samples are drastically weaker once you get up to 20% or so. So the material is very, very weak when it's highly porous, and pretty strong when its porosity is low. We fitted this data to a plasticity model, the Cam-Clay model, a very well-known model, but we made the M parameter in the Cam-Clay model depend on porosity. So this is a hardening parameter that shows how the yield surface of the samples expands as the sample compacts. And for the portion of the behavior which shows this stage 2 linear behavior, we actually got a pretty good fit, an empirical description, admittedly, but a pretty good fit. So we could describe and quantify compaction behavior of these samples, and we could compare them with other people's experiments done using different boundary conditions, uniaxial strain conditions, and so on. And it actually predicted those experiments pretty well. So it's surprisingly general. It applies for the very small strains in the reservoir in this linear region. The strains are only a few tenths of a percent. Okay, so we could quantify the compaction behavior and the permanent part independently of the elastic part, which can be described with a linear approximation or a nonlinear elastic law. So we've got a good fit, and this M parameter, the yield envelope, then is porosity dependent. The porous sample is very weak. That's nice, but I'm a physical processes person. I want to know, why does the stuff do that? And to find out that, what we did some CT work in Grenoble, and that ultimately did produce a very interesting and informative results. But the resolution is still a tricky issue. So what we did was really go back to old-fashioned basics. We cut a cylindrical sample of sandstone in half. We polished the surface with iron beams, okay, and we were able to engrave the surface with all kinds of strain markers and what have you. A thin sheet of soft material in between these things, very thin sheet, reassemble it into a cylindrical sample, okay, and jacket it in a polymer sleeve to make up a kind of simulated intact sandstone sample. We tested it under the same in situ conditions in the triaxial tests, just as we did with the other experiments that I described. So we plotted mean effective stress against porosity reduction. We observed the sample here. We deformed it through stage 1, closing the cracks that are there from damage. Okay. We took it out, imaged the surface again, returned it into the sample, re-deformed it through stage 2, took it out, and so on. So this is a sort of incremental observation of what we could see on the surface of these samples. Actually, we saw really quite amazing things, and I'm just going to show you a couple of those results. So here you see the sand grains, the quartz grains in the sandstone, and here you see clay films that are coating grains, and these are present over the vast majority of the volume of the whole reservoir. It's full of these clay films. Now, this is actually at the beginning of stage 1 deformation, stage 2 deformation that is relevant for the reservoir, okay, the linear part. This is at the onset of that linear compaction behavior. And I'm going to flick to the next shot, which is after deformation, through that linear behavior to a higher stress and strain. Okay, now you see the difference. Now let's go back and forth between them. Beginning of stage 2, end of stage 2. Beginning of stage 2, end of stage 2. You see what's happening here. What is happening is that the clay films between the grains are getting compressed, and they're permanently compressed. So actually, we conclude from this, and we made quantitative measurements which confirm it, the permanent deformation that goes on in these materials is caused by the compression, the consolidation of these clay films, and also shear displacements on these clay films between the grains in the sandstone. That's how this permanent deformation is accumulated. Is that what happens in the reservoir? Is that what happens in the experiments? Yeah, but is it what happens in the reservoir? Well, the magnitude of the strains we got is very, very similar to the measured compaction downhole in the field, to what you calculate from subsidence measurements. That still doesn't say that the process is the same. What we did then, to try to understand that, was we compared the microscopic structure of samples that were actually taken in an exploratory well in 1965. This well here, it's 5 kilometers or so away in Zeerijp. These samples, they were taken in 2015. So 50 years of depletion here compared with no depletion there. And we mapped the density of cracks, if you like, roughly the number of cracks in grains per unit grain area, plotted that against porosity. And what we found was that these two populations of samples here, the red and the blue, are the blue is before depletion, the red is after depletion, 2015. And there is absolutely no statistical difference in the crack populations whatsoever. That means the compaction mechanism that is occurring in situ in this highly seismogenic part of the field, the compaction mechanism is not cracking of the grains. It's not what people see in most experiments on sandstone. It's something else. And our explanation for that is that it is indeed clay films that are deforming. It accommodates compaction in the field and in our experiments. So our experiments should be relevant to describing the inelastic deformation component seen that occurs in situ. We have a constitutive law then, with some sort of physical basis, and if we use that to try to estimate in situ stress development, we can do it like this. We can calculate, just as, let's say, suppose you take that stage 2 behavior, which is linear, right? And suppose you were to assume it was poroelastic, linear poroelastic behavior. You can then calculate, using the equations of poroelasticity, how the horizontal effective stress would change as you reduce the gas pressure in the field. That's what we did here. The initial state of stress is uncertain, somewhere in this range. The linear poroelastic behavior then predicts this kind of development of horizontal effective stress as the pore pressure goes down. And you see it falls well below the few in situ data that there are. Okay, what happens now then if instead of using a simple poroelastic model for this linear stage 2 behavior, what happens if we use the actual elastic part plus the inelastic part, the permanent deformation described by our CAM clay model? In that case, what you see is that, again, there's this uncertainty in the initial in situ stress. Okay, but what you see here is that in the high porosity samples, medium and high porosity samples, you see that this plastic deformation, permanent inelastic component of deformation, strongly increases the horizontal stress development. That's because the sample is spreading sideways. Okay, it pushes our calculated stress development much, much closer to the in situ stress measurements. Interestingly, these in situ stress measurements are made in the part of the field where the porosity is about 20%, which is sort of more or less consistent. It's the high porosity part of the field. So this seems to explain the in situ behavior, the stress development, as well as some of the strains that are measured downhole with optical fibers in the reservoir itself. Right, what does that mean for earthquakes? It means two things. It means we have to take into account this this inelastic or plastic deformation component of the sandstone in calculating the stress development around faults. And we also have to take it into account in the amount of energy that is stored in the sandstone and released when you get a dynamic earthquake rupture occurring. So these are simulations done by one of my students, Luz Bowser. Here you see a fault in the reservoir. The gray is the sandstone reservoir. This is, let's just focus on this one. This is the final amount of shear slip against depth. And here's a fault, okay? And in this case, this elastoplastic model, then, if you like, has been used with the Camclay description to calculate the amount of dynamic slip that would occur during earthquake failure on such a fault. And what you see is that if the thing is assumed to be poroelastic, you get this displacement profile, and it's considerably less displacement, and it's slightly displaced if you include this plastic deformation component. So the modified Camclay model behavior causes less slip and reduces rupture size, and depending on the state of stress. So it has an influence on induced seismicity that occurs. Right, so now we've come to activating faults, okay? And so now we're going to move from sandstones to talking about how the crushed up material inside faults actually responds to these changes in stress that are going on around it. We need to know that if we want to know how the faults activate. What do we want to know? The simplest description, of course, will be something like a static Coulomb envelope. Fine, that will tell us when, it will tell us the state of stress at which faults actually become reactivated, but it doesn't tell us anything about whether that would be silent aseismic slip or seismic slip. Once you reach a stress which is going to activate a fault, how do you get an instability? You have to have either slip weakening, so subsequent weakening once you reach the failure strength, so a loss of strength with displacement, slip weakening, or you have to have what we call rate dependent friction and velocity weakening. In other words, the faster slip on the fault goes, the weaker it gets. This is expressed in this what is very well known in the fault mechanics community, a so-called rate and state dependent friction model, where friction is imagined in the following way, the rate dependence is imagined in the following way. If you're sliding on a fault at a fixed rate, you measure a steady friction coefficient, and then you suddenly increase the rate. Typically, you will see a rate dependence. There will be a direct increase in strength, the direct effect, magnitude A, followed by an evolution effect, B, a reduction in strength till you reach a new level at the new sliding rate. So if you go from slow to fast, and the strength actually decreases, so if B is bigger than A, it's weaker the faster you go. Okay, and so that's going to be unstable, called velocity weakening. A minus B is negative. On the other hand, if you increase the velocity and you get a new frictional strength which is higher, it's velocity strengthening, so you can't get acceleration. So it's stable slip. You don't get earthquakes. Right, so these are the two things you need, slip weakening and velocity weakening, or both, in order to generate an earthquake. And there are rigorous mathematical conditions for how you can do that. What did we actually now try to do? We tried to determine in lab experiments what the properties of these fault rocks are in the stratigraphy. Okay, so here's the reservoir, this is the geological section, this is a simplified stratigraphy. So here is the reservoir sandstone, the Slaughter sandstone, cut by faults like this, typically offsetting the reservoir by half its thickness or maybe even its whole thickness in some places. There's the evaporite with acyl carbonate anhydrite evaporites, a claystone, the main reservoir sandstone, and carboniferous source rocks. These are quite different materials. This is rock salt. These are quite different materials. What is their effect on the frictional strength of the fault, and how does that affect earthquake generation? So we tried to understand this by doing experiments in which we determined low velocity friction, the frictional behavior at low sliding velocities relevant to the initial growth and nucleation of an earthquake rupture. We considered the scale dependence of these properties, and we also considered what happens when you actually get into the high velocity regime. If you produce a velocity weakening material and slip is getting faster and faster and faster, the rupture is going to grow. What are the mechanical properties of the fault rock that determine how the rupture grows and becomes a seismic slip event going at meters per second? How on earth do you do experiments on something like this? You've got to start by going back to nature and looking at what these materials are actually like. The Groningen Reservoir is 3 kilometers under the subsurface in the Netherlands. You can't see it. You can't drill through faults. You can recover core, but if you drill through a fault, you just get lots of broken bits back. So you can see the reservoir where it outcrops. Similar stuff outcrops in the UK, in Germany. And so we looked at these things, and this is typically a fault through this reservoir sandstone, its lateral equivalent. And what you find is that faults are amazingly planar, and they're filled with very, very fine crushed up fault material called fault gouge. This is sandstone on sandstone. This is sandstone on the carboniferous source rock. Very similar, but clay-rich fault rocks. Very narrow zones, and that is our logic for saying, okay, slip is occurring very, very often. You can see in the natural faults in zones of a few millimeters thick, which have been overprinted on each other to make centimeters of gouge. Slip occurring in a few millimeters, we can do direct shear experiments in a triaxial machine at in situ pressure and temperature conditions and measure friction and its velocity dependence. That's what we've done. Here you see some typical results. This is friction coefficient against displacement measured in these direct shear tests. For the sandstone, this carbonate anhydrite evaporite at the bottom of the cap rock, claystone which immediately overlies the reservoir. Here you see these steps in velocity that we've applied. Yeah, 0.1 micrometers per second, 10 micrometers per second, 0.1, and so on. These steps in velocity allow us to determine if these materials are velocity strengthening or velocity weakening under the real conditions in the field. And here's an example. This is for the sandstone. This is an increase in velocity from 0.1 to 1 micrometer per second. You see its velocity strengthening. This is a summary that shows strength profile, if you like, along faults which would cut through these units. This carbonate anhydrite, here it is. This claystone, there it is. The reservoir sandstone, there it is. The carboniferous source rock, there it is. So you see there's quite a substantial strength contrast between these units in terms of their frictional strength. What is the stuff at the top, this stuff, the sandstone, that they're strong. The tambour is weak. Yeah, here's the sandstone, it's pretty strong, friction coefficient about 0.6. Tambour much less, right? 0.35 or so. What is very interesting is this A minus B value. If this is positive, you have velocity strengthening. So you do not have a tendency to nucleate earthquakes, but if it's negative, you do. What you see from this is these materials, when they're in the fault zone, they're only prone to accelerating seismogenic slip when in certain layers, and that's this anhydrite carbonate layer and mixtures. That's what this is here. This is a mixture of this anhydrite plus sandstone, and that's what you see in faults. You see smearing of these different materials to get mixtures. So these two materials can produce velocity weakening and would give unstable nucleation, whereas the others are pretty stable. That suggests that this basal zechstein and the Slochteren sandstone, the reservoir, are prone to nucleating earthquakes. Something else we did, we did experiments where we slide on faults with these different compositions, then stop and let the fault heal. All sorts of dissolution, precipitation, cementation processes go on with time at conditions where we simply arrest the sliding motion, and the shear stress relaxes away at in situ conditions. Okay, and what we did in these experiments, the longest so-called hold experiments ever done on any material, up to 3 months. And what you see here is this is the claystone on top of the reservoir. This would be a fault rock composed of claystone. This does not show any increase in frictional strength with time held when the fault is held static, not moving. Okay, so its strength is totally independent of any sort of healing. There is no healing. It does not show any increase in frictional strength. But the sandstone and this carbonate anhydride evaporite, they show very, very definite re-strengthening or healing. This is the increase in friction coefficient that occurs with simply holding the fault stationary as a function of time. So these samples are regaining strength with healing, which means if you reload them, they're going to go bang again. And as these faults in the reservoir have been inactive since the early tertiary, okay, then the faults will be healed. So it's very, very likely that faults cutting the reservoir and the basal zechstein at the top, they will actually be very strong when they are reactivated and give you a big bang. So again, you'll get slip weakening as well as velocity weakening in these materials. They'll be very prone to generating accelerating slip to generating earthquakes. What happens when you go from these slow sliding velocities to very high velocities? Some of you will know of work that has been done with INGV in Italy, leading the way in some of these developments, high velocity friction experiments simulating natural earthquakes where you have slip rates up to several meters per second, displacements in a rotary shear of 10 meters, let's say, where the samples become enormously heated. They might melt. You have all kinds of thermal processes going on, which reduces the friction coefficient very dramatically as slip presents seismic slip rates. So this is like the post-nucleation phase. You nucleate the rupture at very low velocities. Once it becomes unstable, it accelerates, it starts going meters per second. Then you come in to this dynamic range, okay? So what we wanted to do was measure the mechanical properties behavior of a fault for the real Groningen material, for a simulated earthquake, simulated induced earthquake. And that's what we did. So we did rotary shear experiments. We applied a velocity pulse like this, and up to 1 meter per second over a slip distance of 10 to 20 centimeters. That's like simulating a magnitude 3 induced earthquake. And we did it under reasonably realistic normal stress conditions. And we got results like this. So we found that when you slide this fault at seismic rates very suddenly, then this carbonate anhydride rock at the top is extremely strong and shows a massive weakening effect. The other rocks show more modest effects. The 10 bore not very much at all in these experiments. This again suggests that the clay poor rocks, very strong, show substantial slip weakening like this, but they will be prone to earthquakes. Everything, all the data we have for the sandstone and the carbonate anhydride evaporite and mixtures of them suggests that these will be very prone to earthquakes. I'm going to skip that and just look at this. Here's a seismic section, okay, and this is this basal zechstein anhydride carbonate rock. The yellow is the sandstone. You can see the faults bring these into contact with each other quite frequently. If you look at the statistics of the earthquakes, what you see is there is a skew in the frequency of events towards the top, which would be consistent with some notion that earthquakes are some slightly preferred in these materials which show this accelerating slip type of behavior. And this is another set of data which shows the same kind of thing. This is the frequency of earthquakes against depth. This is still very controversial, okay? But there may be some evidence from the field to support this idea that these rock materials are influence the frequency of events because they're very prone to earthquakes. And all these experiments just too small? Don't have time to tell you much about this. You know, how on earth can you model something at this scale from something that big? A very common problem for us all. This is what we did to try to address that. Went to Japan and did the world's biggest ever gouge friction experiment on sandstone blocks containing crushed sandstone gouge from the Groningen. I don't have time to show you the results. Despite incredible heterogeneities in stress and deformation field, which we measured with DIC, high-speed cameras and all the rest of it, the results we got at the macroscopic scale of 1 meter and 2 meters were exactly the same as at the scale of 5 centimeters. And that's because processes that control it are happening at the scale of millimeters. Another time. What can you do with all this stuff when you have these descriptions of frictional behavior at low velocity and high velocity? You can put them into fully dynamic models, and that's what a couple of my students and colleagues are doing, and actually model the generation of earthquake events. And that's where we are now. So trying to model these things with an improved physical basis and actually see certainly pretty realistic earthquake statistics coming out of this. There's still a long way to go. Elastic deformation in the reservoir is significant. This produces very much enhanced deformation in the center of the field, which is where the seismicity occurs. Sandstone and carbonate anhydrite rocks show this velocity weakening material in faults, and means they're prone to seismogenesis. Slip weakening is enormously important during seismic slip, probably because of thermal pressurization of small amounts of water present in the pores. These data now that describe the real rock and fault behavior, or at least as near as we are likely to get, are now being used to model earthquake nucleation, dynamic rupture, and earthquake statistics. And that all the results suggest that the top of the reservoir is most prone to seismogenesis because of the materials, but also purely because of the stress concentrations. They also are concentrated at the top of the reservoir. Lots of uncertainties, lots of experiments to do in Japan and China still. The big program going on in the Netherlands called DeepNL. And in the meantime, the government has decided to stop producing gas from the field because there's too much damage and people are too upset about it. The big question now is, what happens after the field is totally shut down? Will there be creep effects that will mean we'll get earthquakes? And there's some evidence for that because a big part of the field has already been shut down, and guess what? The earthquakes are still going on, suggesting that the reservoir is creeping. If you want to visit our lab, you can't now because of Corona. Have a look at these films which were made about this project. I'm really proud of them. Please take a look. And there's a few references that you can get from this presentation. Thank you. That concludes my presentation.
Thank you so much, Chris. Thank you very much. Again, I'm clapping my hands, and I'm sure that I'm interpreting what the other would like to do if they were there.
I'm afraid I might have gone on a bit too long, as I usually do.
No, that was 51 minutes. So you promised 50, you delivered it in 51. That was very accurate prediction. Now the floor is open to questions if there is any question. I don't know whether Yannis Stefano is still there. Yannis, are you there? Perhaps no. Yeah, Yannis Stefano. I'm quite sure that you will have it.
How are you?
Please.
Hi everybody. Oh, sorry, I'm trying to activate my microphone.
Yeah, it's working now.
Yes, do you hear me?
Yes.
Hello.
Yeah.
Do you hear me?
Yes.
Absolutely.
Hello. Hi, everybody. Hi, Chris. Excellent presentation. Thanks a lot. It's very nice work.
It's a pleasure.
Well, that was a short question.
I have many questions, but maybe one that comes to my mind is related to this big experiment in Japan.
Yeah.
Which is an astonishing experiment. I was wondering, there's an interface that you already have in the sample, and then you sear it like a direct sear, like a huge direct sear sort of experiment.
Yeah.
Yes, but I don't know if the connection
right.
is good. Sometimes it's a bit it's not stable, the connection. Yeah.
So you're wondering about the influence of the interface maybe and the roughness and stuff like that. Is that what you're getting at, Yannis?
It is something that is, yes, because of course there might be in reality there might be also heterogeneities related to the geometry of the faults at several length scales. Yeah. There might be a damage zone. There might be other length scales that they are apparent.
Yeah. So of course you're right. This is a planar fault, and we also, so our objective here was kind of based on the following rationale, right? In the numerical models of induced seismicity, then the mesh scale is now, for these dynamic models, it's around 30 centimeters. Okay, they're monster computer intensive things. Mm-hmm. It's around 30 centimeters. 5 years ago, it was around a meter or two. So what we were trying to do was see at least, you know, if we quantify friction in a lab experiment on the scale of 5 centimeters, does that at least apply, even in a perfectly flat fault, at the scale of the finite element mesh for the or the boundary element in the describing the faults? And that was just kind of a simple question, and there's all kinds of things that one can question, sub-questions you can add to that, of course. That was what we started out trying to do. And so we did this huge experiment expecting that the state of stress on this planar fault would be pretty heterogeneous. And indeed, that's what it turned out to be. We had it covered in strain gauges and acoustic sensors and DIC dots. And we also measured the distribution of normal stress with pressure sheets and things. And we measured from the DIC, we measured also the heterogeneity of the slip process. What we found really surprised us. We're just kind of about to submit this paper as a paper now. What would really surprise us was that within samples of 1 or 1.5 meters length scale, the heterogeneity in the load distribution, the slip distribution, the shear stress as well, was absolutely incredible. It was different in every experiment, but the macroscopic rate and state friction parameters were essentially indistinguishable from what we measured in lab experiments, even with between sandstone blocks, between steel blocks. We got basically the same results, unless we used polished steel blocks, and then you get different results. So that's what I can tell you about that.
All right. It's very interesting. It's very interesting.
I see that there is a question. There is a question by Jean Sulem. Jean, please.
Jean.
Thank you, Chino. Hi, Chris. Hi, everybody.
Hello,
Thank you,
Jean.
Chris, for the beautiful presentation. I really enjoyed it very much. You mentioned at the end of your talk that the seismic activity is still active, even if the production has been shut down. But what about the subsidence? Is it also increasing?
So it's a bit too early to say for the Groningen field itself. So in 2018, they closed off part of the field where the biggest earthquakes are occurring. Of course, there's still some pressure depletion because of long-range communication with other wells, but it's still far less than it was locally. And earthquakes have continued there. So the sort of the government and public's gut feeling, well, you stop production, stops earthquakes, was immediately sort of upset by the fact that in the couple of years since then, there have been several, I think 3 or 4 magnitude 3.4 earthquakes. So, the earthquakes are continuing. Is subsidence continuing? Is compaction continuing? We don't really know yet. What we do know is that in smaller fields that were shut down more than 10 years ago, that subsidence is still being measured. Of course, it could be to readjustments due to flow in the rock salt, which is pretty thick on top of the reservoir. So we don't know really what's going on there, but in our lab experiments where we saw this inelastic behavior, which we described with the clay model, we did see some rate dependence as well. So now that we're at the tail end of this project now, and what we're trying to do now, and it is very challenging, is to measure the creep behavior of these sandstones under the in situ conditions. Of course, it's very slow, but there does seem to be some creep behavior.
Thank you.
Is there any other question from the floor? Yes. Who's there? Christopher.
I was just wondering if there's any possible thing we could do to stop the earthquake, sort of. If there's anything we could do down, down in the formations, could there be a solution to stopping this?
This is a very exciting question, exciting in positive and negative senses for everybody involved. There have been suggestions that one could try and maintain the pressure in the field by injecting nitrogen, for example, so that you don't deplete the pressure, but you actually remove methane while keeping the pressure more or less constant. Of course, you'd have all sorts of issues like too much nitrogen in the methane and separation and costs and all that sort of stuff. But people have talked about trying to mitigate the earthquakes by stopping the pressure drop and possibly doing something like that even after production. But because the situation, of course, it's a highly complex system. So we're nowhere near being able to predict, for want of a better word, when earthquakes might occur even during the depletion stage. So if you then reverse the state of stress by pumping up the pressure in the field, you introduce another level of uncertainty. So the operating company really doesn't want to go there. So it would be interesting to see as an experiment. It would be a fantastic field experiment, but nobody wants to go there, of course. And what is from a scientific point of view, of course, the changes in production rate, shutting in the field, do amount to a field experiment for us, for we scientists. So it will be fascinating to see what happens and to see if we can explain what happens in future.
This idea of stopping earthquakes is well, there is some colleagues in the floor who thinks that you can control them, and then there is somebody writing proposal about that, and even getting funded for on this based on that idea. But anyway, that would be a long and interesting discussion. I see that people are starting leaving, which is understandable. I wanted just to add one remark. There are two things that I liked a lot about your lecture that was really fascinating. I like simple statements that, in my opinion, are very important. In the first part of your talk, at some point, you said, when discussing that the two sister samples, with the one test that was without cycling and the other with cycle, you said all what is linear is not elastic, and I think this is something that reminds me of a statement that I say every day of my life as a teacher to undergrad, and I think it's so important that we stress that linearity is not elasticity. Elasticity is reversibility. And the second thing that you said that I also liked a lot, when at some point you said that because now you know that this strain is inelastic, you said I'm a physical processes person, and I want to understand what are the micromechanics, the micromechanisms that are responsible for what we call inelastic deformation at the macro scale. And again, this is, I think, a very important approach and a curiosity that I absolutely share. So thank you for those two statements, and thank you for the lecture in general. I think I interpret everybody else feeling in saying that we were lucky, really lucky, and we enjoyed it very much. Thank you, Chris. Thank you a lot.
Thank you very much. I'm only sorry we can't all have a beer together.
Well,
Next time.
the idea would be now to have a beer together, but okay. Please open your email box and you'll find something for you. In the meantime, I'm going to share my screen and show to everybody what I sent you.
That's very kind.
So let's do it. You see, I'm good enough to do it, but I think it's coming. Tell me when you see something appear. Did you see it?
I saw it. Whoa.
Okay, good.
Ah,
so again,
how about that?
well, this is the time of the day in which we are all tired, but we are also very happy, and I hug you when giving you this research medal. Well, I'm sorry that I have to do that online, but believe me and believe us, it's really a very, very well-deserved medal. I'm very happy to give you that. Although this is electronic, so hugs will be in soon, I hope.
It is. It's a real honor. I love it. Thank you very, very much. And when the present crisis is over, we shall get together, have a beer, and do some Italian hugging.
Absolutely. Now, two remarks. The first one, this medal is not golden, so the medal is not gold, just for you not to be disappointed.
Oh, that's
the
okay.
budget of allergy materials doesn't allow that, and that's the bad news. The good news is that you will get the real object. This will be shipped to you, DHL, so you'll get it in a few days. Okay.
Sounds very, very nice. Thank you so much, Chino and all. And it was a great pleasure. And I want to wish good luck to all of the young researchers in your network. It's a very, very impressive group of people. And I'm honored and very happy to have been able to share this time with you.
I think that it's quite time to stop our session. There is just one last announcement that I would like to give you. I'm still using the share screen. Okay, you might see this guy on my screen, Ha Hong Bui, who is a professor at Monash University in Australia. Those of you who are attending the doctoral school were lucky enough to get one of his lectures, and he's one of the lecturers this year. SPH is one of the specialties. Well, Ha Bui has been elected as the one who will play your role, Chris, in 1 year from now. So the invited lecturer for 2021 will be Professor Ha Bui, and we all hope that this will be in person. So if it is in person, Chris, you are already invited to come and join for the beer we were talking about before.
Oh, wonderful.
Okay, thanks a lot to everybody. I declare the session, this afternoon session, closed. And I wish you a good continuation with the doctoral school for those of you who are attending. For all the others, see you very soon and stay safe. Wear your mask. Goodbye.